So let's code Diffusion Gemma from scratch. And this model is really cool. The moment I saw Google release this model and I saw how it works, I was instantly like, damn, this is like actually very cool. And it's very unconventional. Like it doesn't follow the typical style of your LLM because most LLMs that we see are autoregressive LLMs where you predict one token after the other. And it's not really good for GPU and parallelizing and all that stuff because you need to generate one token to generate the next token. The t plus one token depends on the tth token. So that's not really very efficient in terms of parallelizing the compute and things like that. So that's why diffusion gemma comes in. It's very interesting because we generate all the tokens at once. So if I say, hey, what's the color of the sky? And in a normal LLM, let's say the output is this, the color of the sky is blue. So the normal LLM does the color of the sky is blue. Each token comes out one by one. In Diffusion Gemma, what happens is there's a canvas which is initialized with random tokens and it generates all the tokens at once. And this is really cool because you can push all of them on the GPU at once. So you're just pushing the whole output out at once. And it's very cool. So they released this around June 10th of 2026. And it's very cool. It does decently well on most of the benchmarks. Obviously, it's very experimental territory. It's not set in stone because nobody really does diffusion based generative text generative models, right? Just a small heads up. This model takes in both vision and text as input modalities, but we will be looking at only the text part. I'm not going to code the vision encoder part of this model. You can maybe try that out on your own. I'll be coding the text part, and I think it's pretty cool. It's very important to understand that the technology that goes behind these things. These are the benchmarks. Obviously, I would say it's slightly cherry picked. It's not the best numbers that you can probably see, but I still really believe that there's a lot of merit in the idea that goes behind a model like this. This is something which Unslot did, which I found very cool. So what they did was they gave a Sudoku puzzle to the model, and they asked the model to essentially just solve it, right? And in a traditional autoregressive model, it finds it hard to do this because you need to predict token by token, right? And here what happens is whatever position was missing, it just fills it in one shot, right? And obviously, it goes through multiple denoising steps like any diffusion model, but it still happens parallelly. All the tokens come out parallelly, so that's pretty cool. Now, let's look at what the model does, right? Let's see what the model does. So you can see an example here. The model, an autoregressive LLM or the AR LLM, it picks one token at a time. And this is not really cool in terms of a GPU utilization perspective. In a diffusion LLM, we have these random words which start in the beginning, and over multiple denoising steps, we denoise all of them and we come to the conclusion of whatever tokens we want to give as an output. Let's look at how the model works first, and then we can get into like the nitty-gritty details of all the small components inside this model, right? And just to give a disclaimer, if I've made any mistake in this video, I'm really sorry about that. It's just a fun weekend project that I did. I just put together the whole code. The idea of this video is going to be a long one, and the idea of this video is to go through all the fundamental concepts that are used inside a state-of-the-art LLM, right? There are a lot of concepts in this which are directly copied from Gemma 4, and Gemma 4 is pretty good. Like Gemma 4 is one of the frontier open source LLM models, right? And a lot of lot of layers and a lot of concepts like MOE, mixture of experts, and routers and text embeddings, rotary positional embeddings. All these concepts are basically kind of, I wouldn't say copied, but inherited from Gemma 4. And we'll be coding all of that. So the idea is this video will be a self-contained video of pretty much most of the state-of-the-art technologies that go in, and we'll be coding all of them from scratch. And when I say scratch, we're not going to be coding like the back prop and the front prop and things like that. We'll be using minimal Pytorch code like linear layers and activation, simple activations and things like that. We'll also follow the flow of the tensor, which allows us to see how the tensor transforms over layers and what happens and things like that. So let's see how this model works first from a very high level overview. This is not getting into too many details. So let's say the input is, hey, do you like coffee, right? And this is a typical 5 token input. Now this goes into an encoder, which has 29 layers, and each layer of the encoder caches its key and value, right? So since obviously these models are transformer based models, and each of these models have the multiple layers of queries, keys, and values where we calculate the attention of self-attention. We cache in the k and v values for all these layers, right? And then what happens is we have a decoder where we initialize random tokens. So how, what, hey, the, sky, these have nothing to do with, hey, do you like coffee, right? These are just random tokens from the vocabulary. So the vocabulary can be huge, right? 65,000 words, tokens and whatever. So we initialize the canvas, and that's what we call a canvas. We fix the length. So here it is 1, 2, 3, 4, 5. So here's 5 length canvas, and we initialize this canvas with random tokens. Then we have the decoder. So again, the decoder again has 29 layers, just like the encoder. And what happens here is each layer reads the K and V from the encoder cache. So the layer 1 of the encoder caches its K and V value. The layer 1 of the decoder reads from this cache and uses the K and V value in its attention calculation, right? It's not really cross attention. It's a little bit different from cross attention, and we'll see why. Now let's say it gives an output. So it goes through, it takes the random canvas, it passes that through the decoder reads from the encoder, and finally we take the output. Now the output is a denoised state of the tokens that we have given as input. So let's say we have yes, what, hey, like, coffee, right? So the question that we asked is, hey, do you like coffee? The typical answer is yes, I do like coffee. If you don't like coffee, you're probably a weirdo. But anyway, let's look at the output, right? Yes, what, hey, like, coffee. Now, it's 5 tokens. It's a 5 token input and a 5 token output. Here, yes is correct. That's the correct token that we want. And like is also correct. So we lock in these 2 tokens. And what we do is we pass on the tokens that we are not certain about. We pass that back for the second pass through the decoder, right? Like that, we can do it 48 number of times or until we see a stop token. And this is customizable. We can do it 10 number of times. So the number of denoising steps is something that we can set. It doesn't need to be 48 all the time. And obviously the quality of your output will depend on how many denoising steps you have. How do we decide how to lock in these tokens though? What we do is we have confidence associated with each token, right? That's just how an LLM works. Each token has a confidence associated with it. Now, the higher the confidence, the lower the entropy, right? Because entropy means how uncertain you are about something. So the higher the entropy, the lower the confidence, because the higher the uncertainty, and the higher the confidence, the lower the entropy. So let's say yes and like had really high confidence, right? Which means both of them will have very low entropy. And let's give random numbers. These numbers are not, they don't mean anything, but they're just random numbers. 0.05 and 0.01. Now, what we do is we decide something called as an entropy budget. Let's keep it 0.1 for now. And now we write these tokens in ascending order of their entropy, right? So that if we write them in ascending order of the entropy, like, yes, coffee, hey, what? This is the ascending order of the entropy. Now, we keep doing a cumulative sum. So that means we keep adding in this direction until we reach this budget. So 0.01 plus 0.05 is 0.06. But then when we add 0.19 with 0.06, we exceed the budget, right? Because this in itself exceeds the budget. That's a different thing. So we cut it off and we accept all the tokens which lie within our budget. So we have yes and like. So that's why we have locked in these 2 tokens here. Now, so Now what happens is coffee is technically a correct token, right? You can see the entropy is less, but it's just not less enough to come within the budget. That's why we're not accepting it. Technically, the output needs to be yes, I like yes, I do like coffee or something like that. Coffee is technically the correct token here, but we're not accepting it because it's still it does not fall under this cutoff of whatever budget we have set. So 0.1 to 0.01 plus 0.05 is less than 0.1. So we accept these two tokens and we renoise the rest. So what happens is for this token, and this token, we renoise it and we send it back to the decoder for the second denoising step. And then we get the output, we check for the entropy, and we go for the next denoising step. And we keep on doing this for like 48 times or whatever. Now, there's something interesting here, and that is the self-conditioning block, which we see even here, right? Something called a self-conditioning. And what is that? Um, Self-conditioning is how the model conveys what it was pretty confident about, but not fully. So for example, here coffee is something it's pretty confident with, right? But the model is kind of confident about coffee, just not enough for us to accept it yet. That's where self-conditioning comes into play. Self-conditioning allows us to convey this to the next iteration. So when we go to the next denoising step and when we renoise these tokens and give them back, we can convey to the model that the model was kind of confident about coffee but not fully, and this information gets conveyed through the self conditioning. So we have an input, we have self conditioning, and then it goes through the decoder. So now the decoder knows what happened in the previous iteration. It's a way to infuse this information into the next iteration so that the model is not completely coding the whole thing from scratch all the time. The model needs to understand that it's in a loop of denoising and it needs to improve the outputs over time. So that's where self-conditioning comes into play. So is how we this is how diffusion Gemma works, right? So it's an encoder, it's a decoder which has self-conditioning, right? The reason it's called self-conditioning is because it's the same, it's technically the decoder is looking at its own output from the previous iteration. So it's called self-conditioned. So the output is conditioned on itself. That's what it's called self-conditioning. So this is an overview of how the model works. Now let's get into the nitty-gritty details. Let's define each layer inside the encoder, inside the decoder. And fun fact is the decoder and the encoder are pretty similar because essentially they are just attention modules, right? So they are pretty similar. The only different, there are just very minute differences in terms of how the decoder reads the KV cache and the encoder does the KV caching, and the decoder does not really change the KV cache in itself. And there are very small differences like this, but for the most part, all the modules used inside the encoder and the decoder are the same. Let's look at the easiest part of this entire process, that is the normalizing layer. So the norm we use in Diffusion Gemma is the same norm which we use in most of the popular LLMs these days. That is the RMS norm. And what RMS stands for is root mean square. And I think you can see that here very clearly as well. It's the root of the mean of the square. So if we have a certain hidden state like this, what we do is we square it, we calculate the mean, we add a epsilon just to prevent, because we are going to divide with it, so we don't want it to be zero and we want to prevent the zero from pushing the output to infinity. We add this epsilon, which is usually 10 power minus 6 or some very small number like that, and it's just a stability parameter. And once we do this, we scale the edge with this value, and then we multiply it with a learnable scaling parameter. So this gamma is nn dot parameter. So it's a learnable parameter which can scale the output, right? The whole reason we do a norm is so that we can have a certain control over the magnitude of all the outputs, all the numbers that can come in a layer, right? Currently, if a layer has just because for some reason it has an output like 200, right? We don't want a model to see a number it has never seen. So the norm layer is essentially a way where we learn how to scale the output uh, at a logit level, where we can control the output of each layer, and we can essentially not surprise the model with random numbers coming up suddenly. So The norm is just that, and RMS norm is what we use in most of the attention modules. For example, VIT, the Vision Transformer, uses this. The Llama family of models use this. The Mistral family uses this. Most of the popular LLMs, DeepSeek uses RMS norm. Most of the popular LLMs we see use RMS norm. Let's also look at the code, right? Let's see how the code works for each concept. Let's look at the concept, let's look at the code, and eventually we'll see how they all come together to form the beautiful model that we have. So the code is pretty simple. We just declare the epsilon first, we pass it as an input, and obviously all the modules in this will inherit from an n dot module because we don't want to define too many things manually. This takes care of the backprop and things like that. So we define epsilon, we mostly give a very small number here. Width scale is simple, it's nothing too complex. We'll see what it does. It's just a multiplication which scales the output. That's the gamma parameter which we talked about here, this gamma parameter. So it's an nn dot parameter, which means we are essentially creating a learnable parameter within the model. And what happens is if we get a hidden state, we do hidden state power. That means we raise it to the power of 2, which is the square. And then we do a mean along the last dimension because the information is generally in the last dimension, right? And then we add the epsilon. So that is basically this part. And then we have the forward function where we essentially get the output, we norm it, and if width scale is true, then we multiply it with gamma, which is the scaling parameter, which is what we defined here as width scale. The reason I define it as width scale is because that's how it's defined in the gamma's state dict, right? So we'll be loading the model in the end, and we'll be inferring the model to see how it works. So we need to keep the state dict the same, otherwise I'll have to write a code to remap the state dict completely with my current design choices and things like that. We don't need that. It's very complicated. So we have this. So we multiply the output with gamma and we return that. Pretty simple. One very important thing in the code here is the float. We have two floats here, right? We do hidden states dot float and hidden states dot float. Why do we do this? It's a very interesting question to ask. Let's look at an example here. So we define the RMS norm. 10 power minus 6 is basically our um, epsilon value, and we give 4 as the dimensions. Now, hidden state 1 is just a random torch tensor 3140, just like how I declared here. Now, we pass this and we see what the output comes out as, right? And we give both the inputs as float 16s. If we have not given this float, then this float 16 is going to become a problem because we generally so what dot float does is it upcasts your output into float 32. So if you give float 16 as an input, there might be certain numbers which might not fall in the range of a 16-bit float, right? We need a 32-bit float to deal with those numbers. So, and a norm is something that you use in a model to be able to control these magnitudes, the sudden explosion or a sudden decay, anything like that. So a norm should be sensitive to all these things. So if we are using float 16 as the model D type, there will be a big problem when we try to load this um, RMS layer and suddenly we see a number that does not lie within the range of float 16. And that's why we do float 6. That's why we do the dot float here. So this is pretty simple. We just looked at two examples. So what happens here is that if we give 3 minus 1, 4 and 0, and if we give 300 minus 100, 400 and 0, we see that the norm of both remains the same, right? Because these two tensors essentially are conveying the same information. They just belong to different scales. And we don't want that. We don't want the magnitude of a number to dominate the calculation. We want the representation to magnitude the calculation. So what we do is we calculate the norm and we essentially normalize these layers, right? Now, so here I have a commented example. You can uncomment this and run this and see for yourself of what happens when you don't do the dot float here, right? There's no dot float here. So what happens when we don't do that? You can just uncomment this and see what happens and you'll understand what I mean by that. So we can see how both the norms of both the inputs that we have given here both correspond to the same number, And that's what we need. We don't want these random magnitude changes to dominate the norm layer, right? So that's about it. That's about it with RMS norm. It's pretty straightforward. It's the most simple part of this model. So let's go to the next part. That's the token embedding layer. And this part is really important. This part is something that you'll find in every LLM, or to be fair, every language model, because every language model needs something that converts a, a token into an embedding, right? Because I love coffee makes no sense to a model like it makes to us. So we need to find a way to represent I love coffee, which are three tokens, in a way that makes sense to the model, right? So we convert these into matrices or vectors, and these are called embeddings. Let's look at this example. Say we have a vocabulary size of 6, and this is our vocabulary, right? I, you, love, coffee, tea, too, right? So there are like 6 words and 6 tokens to be more precise. And each token gets these IDs, right? So the ID of I is 0, ID of you is 1, and so on. So if I give an input like I love coffee, what happens is we are taking this, we're taking this, and we're taking this. But we cannot give the input to the model as 0, 2, 4, right? Because then the magnitude starts dominating, and 0, 2, and 4 don't really represent I love coffee. So what we do is we create an embedding layer, and Torch already has this within the NN module, that is the NN.embedding. So what embedding layer is it's something that maps a vocabulary size to a dimension that we want, right? Let's say the dimension is 2. So what happens is there are 6 possible tokens in our toy scenario, and each dimension is 2. So what happens is we make a 6 cross 2 matrix where each token has a two-dimensional representation, right? So let's say I becomes something like this, right? 0.05, 0.2, something like this. These numbers are random, but every token gets converted to a two-dimensional embedding. This is then given to the model, because now what happens is these two numbers come together to form the representation of what we mean when we say I, when we say the word I or the token I. This is just a way to allow the model to understand what we're talking about. And of course, these numbers are just purely for explanation, and we obviously need much bigger numbers when we're dealing with actual real world large language models. For example, the vocabulary of submodels like GPT and things like that, they go up to 250K, right? 250,000 tokens, unique tokens. Let's look at how this works in our scenario, our Gemma, diffusion Gemma model. So there's something what we do here, that's the text scaled word embedding. It's not just the word embedding. We do a small scaling to it. And the scaling is just multiplying it with a number of our choice. Let's say embedding scale is 1, and we can set this number to anything. But what happens is in the end, we multiply our embedding with the embedding scale. So the code is pretty simple, and what happens here is in Diffusion Gemma, the embedding layer is copied directly from the Gemma 4 family of models. So what we do is we define Gemma 4 text scale embeddings, and all we do is we just inherit from that class. That's it. It's exactly the same. So this is the embedding, the actual embedding scale value, which is 1, or it can be 8 or whatever. And what we do is we register this as a buffer, right? So what register buffer does is every model, right? When we train a model in Pytorch, we do something like saving the state dict to load it later and things like that. So when we register a buffer, that means we want this parameter in to be used inside the state dict of the model. But what persistent equals false does, by when you set persistent to false, what this does is that it does not save this into the state dict, but it loads it in real time when you load the model. Right? So when I load Diffusion Gemma, this buffer, this embedding scale does not get loaded from the state dict, but we can load it from the config or from anything like that. And what this does is it inherits from NN.embedding, and the forward is a super of the forward of the parent class. That means it runs the exact same logic that is used within the NN.embedding's forward layer. The only difference is it runs the forward and then it just multiplies it with the embedding scale value that we have set. So let's look at a very simple example. Let's set the same vocabulary 6, 4, and pad index is something that we use when we want to exclude it from the gradient calculation. Is when we have a sentence of 4 tokens, but we need it, the model accepts inputs only of 5. So what we do is we append a padding token to it, and the padding token is just a placeholder, so it doesn't really contribute to the learning. So what happens is we don't want the gradients to, like, let's say the model predicts a pad token. We don't want the model to be rewarded for that. So what NN embedding does is it provides us a way to give the padding index so that we can pass that to the model and make sure that the model does not use it in the gradient calculations. So let's say we create the class and we pass an input of 1, 2, and 3. Very simple input. What we do is so vanilla stands for a simple embedding, like the typical embedding you'd use in a transformer. And we have the text scale embedding, which belongs to our diffusion Gemma and the same as Gemma 4. Now, we set the scale value to 8. This is just a random number. It has no correlation with the actual model. We can set this to anything. Now, we look at the vanilla output and we look at the scaled output, right? So the vanilla output is when we pass these 3 tokens to the normal embedding layer, and the scaled output is, and the scale out is basically what we get when we pass this through the diffusion Gemma embedding layer. So the vanilla output would come out as something like this. So what we have set is the dimension is 4, right? So each, and we have given 3 tokens as input. So each token gets a 4-dimensional representation associated with it. And that's how the model is able to recognize what each token means. So this is your vanilla output and this is your scaled output. So if you can see, it's pretty straightforward. If you take this number and multiply it with 8, which is basically what we have set as our embedding scale. So if you multiply it with 8, we essentially end up getting this number. And we can see that if you divide this, if you divide this with this, you essentially just get a matrix of all 8s, because essentially this matrix is just what we get when we take this matrix and multiply it with 8, because it's as simple as that. Now let's move on to one of the most crucial parts in LLMs, that is the positional embeddings and rotary positional embeddings, also popularly known as rope. This is the state-of-the-art positional embedding strategy that's used by almost every modern popular state-of-the-art LLM. Initially, we used to use sinusoidal positional embeddings, and for in models like VIT, the vision transformer, we use static learnable positional embeddings. But in almost all the LLMs, in almost all the modern LLMs, we only use rope. Why do we need rope? Let's understand why we need a positional embedding to begin with, right? Um, so we have all these tokens which are going into the model, and self-attention allows each token to communicate with every other token, right? But and the embedding layer is essentially something that conveys the meaning of each token, right? So I love coffee are 3 tokens, and the embedding layer allows us to convey the meaning of these tokens to the model. We need positional embeddings because we need to find a way to convey the order of the tokens to the model as well, right? Because I comes before coffee. I mean, I comes before love and love comes before coffee. So these 3 tokens are arranged in a sequence, and we need to have a way to convey this information of the sequence ordering of these tokens to the model. And that's where positional embeddings comes into play. We find a way to give we find a way to infuse the positional information into the embedding so that the model knows which token is where, right? How do we do this? Very interesting. If you're new to LLMs and if you're new to attention, it's a very interesting concept, because I feel like a lot of people, when they read about positional embeddings, they just accept the formula and move on, and they don't really question why we do this and like what's the point. And because the formula for sinusoidal and rotary rope both are pretty complicated, right? They're not very intuitive from the first glance, but most people just accept the formula and move on. But there's very, very fascinating ideologies behind it, right? So let's look at let's set up the problem and let's solve it as we go. So I love coffee too, right? So these are essentially four tokens that we have. And from here, we know the token IDs of each token from the vocabulary that we have. So I is 0, 2, 4, and is 5. Once we pass them through the embedding layer, we had decided that the dimension's 4. So each token gets a 4-dimensional representation in it, right? So the 0 gets this, 2 gets this, and whatever. So each token ID gets its own 4-dimensional representation. Now, what rope is trying to do? Let's try to understand what rope is trying to do, and then let's see how it does it. We want to rotate each embedding at a specific angle, and this angle encodes the positional information, right? So if we rotate the first token at a certain angle, and then if we rotate the second token at a certain angle, and then the third one at a certain angle, and the fourth one at a certain angle, we are essentially, and when we rotate, when what I mean by rotation is that we change the value inside the tensors, because obviously initially it sets something and then we rotate it, right? So what happens is when we rotate all these tokens at all these angles, and then when we give it to the model is obviously a very high dimensional uh, black box for now, right? I mean, we'll obviously not be talking about it as a black box in the video, but what happens is we are infusing the positional information, right? Because the first token is at theta, and the next token is at some theta plus something. The third token is at theta plus something plus something. So the model is, look, when the model looks at these tokens, it's able to inherently see their ordering because each token has a different angle. So the idea of rope is to rotate each token so that we can essentially infuse or encode the positional information into the token itself. Now, very interesting, sounds very cool. How do we do this? Now, we have a dimension of 4. So how do we rotate a 4D tensor, right? Because rotation, by definition, is a 2D operation. When you look at the idea of rotating, it's a 2D operation. It's you can't rotate a point, you can't rotate a 4-dimensional. You can only rotate a 2-dimensional object. You can a line essentially. How do we do this? For example, if you have to rotate x comma y, and if you want to rotate it by some angle theta to get x dash y dash, the way we rotate it is by multiplying this x comma y matrix with this rotation matrix, right? This is generally in math called a rotation matrix, r of theta. So this matrix is simple. It's cos theta minus sine theta, cos theta. And this is basic math. It's just algebra. So if you multiply these two together, you will see why it makes sense, right? I don't want to go around about explaining it. It's pretty self-explanatory. And if you want to derive it yourself, it's very simple. Just take a vector xy and rotate it by an angle theta and find out the new x dash, you get x dash y dash. Now all you need to do is find a relationship between these two vectors, and you will end up with this formula. It's a pretty straightforward formula, and it's used in math all the time. So we know we can rotate a 2D vector, and it's pretty straightforward. But what we have here is 4D. And when we look at these models, when we look at these LLMs, like in production and things like that, it's 1,000 dimensions, 1,024 dimensions, 2,080 dimensions, and things like that, right? So how can we do that? So what we will do is each token is a 4-dimensional representation. So we'll break them down into pairs of 2, and we will rotate the pairs. So this is the first pair and this is the second pair, and we'll rotate them individually. So we will rotate the 2D parts separately, but by how much is still a question, right? We have, let's say we have n number of dimensions. We'll split them into n by 2 because we are pairing them, right? And we'll be rotating each pair. But the question is, how much do we rotate them by? Because once we break them into pairs, now we have a big problem. We have increased the problems that we have actually. Initially, we just had to rotate a token. Now we have to rotate pairs and make sure that we also convey the information of which pairs belong to which token. Because the first pair here let's go for this. This pair belongs to I, and this pair belongs to I. But if we look at another pair, this pair belongs to love, and this pair belongs to love. So now when we rotate these tokens, we need to make sure that we also explain which token the pair belongs to. And that becomes another thing which we need to compute now. So that's these are the problems that we face. How do we decide this angle? Because this angle has become now the only way we can encode this information and give it to the model. But now we have two problems. How do we do it? The angle needs to convey token position and embedding position. So the embedding position is which pair, which token it belongs to. I mean, which where is this pair in the embedding, and the token position is which token it is. So that's where the frequency or omega comes into play. And the easiest way to understand this is by looking at a clock. So I really want you to follow with me along on this concept. Let's try to solve this in a very like by using an analogy. Every day we have 24 hours, and our clock has only three hands: hours hand, the minutes hand, and the seconds hand. What we need to do is and all these three hands of the clock move at different frequencies. The second hand is the fastest hand, the minutes hand is the second fastest hand, and the hour hand is the slowest hand that we have. So when the seconds hand completes 60, the minutes hand moves by 1. When the minutes hand completes a 60, the hour hand moves by 1. But for us to tell the time of the day successfully, we need a combination of all the three hands that we have. So now, if we have, let's say, an example where we have 7, 15, 30, 8, 15, 30. So two hands are same, but this R's hand, which is different, completely changes the meaning. So even if two hands are the same, the combination is what creates the meaning. So this is the best way to understand this, how rotary positional embeddings work. And each hand has a different frequency because of which the combination of all the three hands gives you the correct time of the day. We'll do the same thing for the tokens. We have to encode which token it belongs to, and within the token, which pair it is. So each gets a different frequency. And because of this, when you combine all of them together, we'll be able to protect the individuality and still convey a different combined meaning of all of this. The combination of all three frequencies is what makes time unique. Let's look at an example. 4 tokens with 6 dimensions. Let's not do 4, let's do 6 so that it's a little easier to calculate. Now, for simplicity, let's take the same token. So we have 4 tokens of you, and you. So it's the same token. The embedding remains the same is what I'm trying to say, because obviously they mean the same. So we just need to infuse the positional information. For example, this U comes after this U, and this U comes after this U, and this U comes after this U. So we just need to, the tokens are the same. We just need to infuse the information of the position of these tokens. How do we do this? So we said the dimension is 6. So a 6-dimensional tensor. So let's just take 1, 1, 1, and 1, and 1, 3, 4, and 1. So let's just take a simple one example. So obviously the embedding will be in decimals and they'll be all different from each other. But this is just for explaining, right? Let's take this, and now we need to add the rope to this. So one thing which Diffusion Gemma does a little differently from what I explained is that here I explained how the pairing is essentially these two with these two and these two with these two. Uh, it really does not matter how you pair as long as you keep the pairing consistent. And this is a very important point. It's not something to just skip through. The pairing of your embedding values do not matter as long as you keep them consistent. Diffusion Gemma does a different style of pairing where this one gets paired with this one. So, and this one gets paired with this one. and this one gets paired with this one. This is for computation because what happens is we can just split the embedding in half, and then we can just pair the first element, second element, and third element with each other. So this is a very GPU efficient pairing, and that is the only reason why we're doing this. There's no other reason to it. It's a pure design choice, and it has no mathematical significance. It even if you pair this one with this one, as long as you keep it consistent, you will still get a model that works really well. It's just that this way of pairing makes more sense from a computational perspective. Now, we have 6. The dimension we have chosen is 6. So 6 by 2 will become 3. So we have 3 pairs of tokens. We calculate the frequency of how much we need to essentially rotate these pairs by. So this is the formula for calculating omega, and some people call this inverse frequency as well. The reason they call it inverse frequency is because we do a 1 by. We're not doing 10,000 to the power or something. 10,000 to the power of 2i by dimension is just a way to calculate a small number. Because 10,000, we'll see, and we'll see why this makes sense. 10,000 is what we define as the base of your rope. Base is essentially 10,000. We can take any number. 10,000 is just purely empirical and it really works. It provides a very distinct number of frequencies. So 1 by 10,000 to the power of 2i divided by dimension, right? And let's substitute uh, all the 3 different values of I. I goes from 0 to dimension by 2. I goes from 0 to 2 because we don't include 3. 0, 1, and 2. So there are 3 pairs. So we have three I values, and we calculate the omega for all the 3 I values. So omega for 0 is 1 because if we substitute 1 here, if we substitute 0 here, we just get 1 by 1. Omega 1 is again straightforward. You just substitute the value of I here. So I becomes 1. So you have 2 by 6. 2 by 6 is 1 by 3. So 1 by 10,000 to the power of 1 by 3, and it approximately comes out to like 0.04 something. Omega 2 is, again, you substitute I of 2 here, and dimension is 6. So 2 2s are 4, 4 by 6 is 2 by 3. So 10,000 to the power of 2 by 3, and we get something like this. So now we have 3 frequencies with us. We have 1, 0.4642, and 0.002154. So this is the closest analogy we get to the clock, that clock analogy that we had. This is the hours, this is the minutes, and this is the seconds. And all these frequencies combine together to convey what the unique time is. So when we convert that analogy to our situation, all these 3 frequencies together combine to tell us the unique position of a token, or the unique position of a token. So there are 2 types of rope that we use in Diffusion Gemma. One is the default rope that we just calculated, and the other one is a proportional rope. And again, this is a design choice. I'll explain how it's done. So what we do is we define something called as a partial rotary factor. And in Diffusion Gemma, it's 1 by 3. Okay. What we do is we calculate how many embeddings we want to apply rope to, and then we apply rope only to those positions. And there are certain positions where we do not apply any positional encoding. So the information that those embedding locations have are purely information of the tokens, and they have no positional encoding whatsoever. And there are a lot of viewpoints about this. If you ask people, some people say it's a regularizer. Some people say it's like, you drop out certain positional embeddings in certain place because the values of those angles it gets rotated by are very small, and they don't contribute much to uh, you know the computing those values don't really contribute much to the positional embedding. So there are a lot of different opinions on this, and I personally feel like I agree with the second option, because sometimes the angle with which you rotate the tokens are so small that you might as well not rotate it, and it won't really make a big difference to your output. So these angles are called as NOPE, that is no positional encoding. So we calculate how many embedding positions you want to apply the rope angle to, and that is determined by dimensions multiplied by this partial rope factor that we have, and we integral divided by 2. So 1 by 3 is that, as we discussed, the dimension is 6 for our small example, and integral division by 2, which gives us 1, which means only one frequency will exist and the others will be set to 0. And since we have 3 pairs, 2 of them will be 0. 2 of those positions will not have any positional encoding associated with them. The formula remains the same, there's no difference. It's just that I only goes for 0 and I is not calculated for 1 and 2. So omega 0 becomes 1 and omega 1 and 2 becomes 0. So we have these 3 frequencies here. Now, these angles are associated with the position within the embedding. We need to know the embedding belongs to which token to begin with. And the raw position of each token is 0, 1, 2, and 3. So in a very simple example, if we look at this, the position of this is 0, the position of this is 2, 1, 2, and this is 3, because they come after one another. So a 0 index list will have 0, 1, 2, 3 as its raw positions. Now, what we do is we take the frequency that we calculated, that is either this or this, and we multiply it with the absolute position of the token. And this combination of frequencies multiplied with the position of the token is what gives us the unique angle for each token, right? This is what rope does. So we find an angle which can represent two things: the position of the embedding and also which token that embedding belongs to. This angle is what we substitute here, and we use the typical rotation formula that we have, where we break down a vector into pairs of 2 so that we can then apply this rotation formula and rotate all the pairs individually. So this bakes in the positional information into all tokens by rotating them, and that's why it's called rotary positional embeddings. This is a very crucial topic to understand, and understanding this is very important in terms of all this, understanding all the SOTA models that we have today. Let's look at the code. The code is a little complex, but it's pretty straightforward when you compare it with the algorithm that we have. So rotate half is basically something that allows us to pair it the way Gemma wants us to pair. Because as I said, Gemma does not follow the typical pairing of this gets paired with this. Gemma likes to pair this with this. So we rotate half, as in we take the we take the vector and then we just rotate it by half and put it against each other. And then apply rotary positional embedding is just the part where we apply the sine and cos, and that's the formula that we just saw, right? The matrix formula, and that's literally what we're seeing here as well. Now, one very crucial thing about rope, and we'll see this in the model later as well. Rope is only applied to queries and keys. They are not applied to values, and we'll see why. It's just the typical design choice which people follow. We do not apply rope to values in the model. We'll see that when we define the model. Now, we have a code for computing the default rope. That's what is used by certain layers in the diffusion Gemma model. And then we have a code for computing the proportional rope. We compute the rope number of rope angles, and we compute and the rest of them are nope angles. Once we calculate the inverse frequency, or omega. That's what we defined earlier. And it's pretty straightforward. 1 divided by the base, which is 10,000, to the power of I by 2I by dimensions, right? And it's pretty straightforward. Torch.arrange creates an array of values which are between 0 and dimension, and they are of 2 gap, right? And we divide that with the dimension, and that entire thing goes into the power of the base. And the code is very self-explanatory. If you have followed through the theory part, the code is literally just a translation of it. And in the proportional rope, we can see the same thing. We get the base value, we get the rope proportion, that is in our case 1 by 3, and we have set the default value to 1 where it doesn't really do anything. But yeah, we calculate that, and once we have that, we calculate how many frequencies we want to calculate to begin with. And that is the proportions multiplied by the dimension with an integral division of 2. And We to calculate the nope angles, we just subtract the number of rope angles from dimension by 2, right? It's very straightforward, because if for n number of pairs, if you're going to apply the rope to two pairs, then n minus 2 are nope pairs. And that's basically what's happening here. And this is just a case where, if there are no nope angles, then we need to basically apply it for everything. And that's basically what's happening here. And this code is very self-explanatory. Now, let's define the class for Diffusion Gemma text rotary embedding, because all these are just standalone codes. We need to integrate them into actually useful classes. So we check which layer type that we're dealing with. For example, we have two layer types here, sliding attention and full attention. And if you look at the config, we can see that full attention has a proportional rope and sliding attention has a default rope. And both have, this one has a different theta as well. But anyway, that's not really very important. Now, we check which layer we are applying rope to, and based off of that, we calculate the buffers. And here we have persistent is false again. We're not saving this into the state dict, but we're calculating all the frequencies beforehand, and we're just keeping it ready. And whenever we get the model and we want to do a forward pass, we're just going to multiply. We're going to just apply the rope and move ahead with it. Now, um, and different layer types have different attentions, as we discussed. So we calculate all the inverse frequencies based off of which rope type that we want to do, default or proportional, and we save all of them as register buffers, and persistent is false, so we're not saving them to the state dict, right? Now, the forward pass is very simple. There's no learning that really happens in rope. It's literally a static value that's calculated. We calculate the inverse frequencies, and what we do is we just read it from the buffer that we are saving. And once we have that, we change the dimensions so that we can multiply it in batched form and things like that. And once we have that, we just get the cos and sine values for all the possible tokens for all the length that we have decided. And we just return the cos and sine values based on which layer type and what position IDs we are dealing with, right? And the model essentially will give you what position ID we are dealing with, and the model will tell you which layer type we want. So we can just call this function and immediately apply, just get rope and apply it. The code, obviously all the code is made available on my GitHub, and you can, this Git repo is open. I'll link it on the description as well. You can see the entire code here, and this is just some diagrams that are there. But yeah, so if you expand this cell, you can see a step-by-step calculation of the same example that I described in my iPad. I explained this simple example with 1, 1, 1, 1, right? And this is the same example, and you can see a complete hand-calculated version of this, where you can go through each step and see what transformation happens and how the code which we just wrote above works. And this is just a step-by-step dissection of the same. So now we have done RMS norm, we have done the text embedding, we've done rope, and these are three very crucial things. Now the next thing, we have something called as grouped query attention. I hope people are familiar with what the normal attention is, the QKT, softmax of Q multiplied by K transpose multiplied by V, and the scaled version of that where we essentially divide with the dimension of the query and whatever, I mean, of the key and whatever. So I hope you're familiar with that. If you're not, you should probably check that out first, because this is a version which is slightly a modified version of that. Now, and also, I hope you're familiar with multi-head self-attention, and not just the vanilla self-attention where we break down the queries and keys and values into multiple heads and then perform the attention calculation. Uh, if you're not, please go through that. Let's understand what this is, right? To calculate multi-head attention, we need Q, K, and V. Simple. There's nothing too complicated in that. We have Q, that is batch size, sequence length, hidden dimensions, and we break this into multiple heads. So this big tensor becomes this, right? Where it is batch size, sequence length, number of heads, and hidden dimension per head, right? So I should probably, this is head dimension and this is hidden dimension. They're different things, right? I hope all that stuff is clear and I don't need to explain all that. Um, So we so what happens is whenever I write mh, that means multi-head. So v multi-head and k multi-head, that is the value in multi-head form and the key in multi-head form, right? So all of these tensors get split in the same way. The query, key, and value get split into multiple heads, and then we calculate the attention, which is basically just a softmax of the q k transpose divided by root d. And root d is essentially just a scaling factor. It's basically the dimension of these tensors, of this query, key, value tensors. But in group and in normal multi-head attention, the number of heads are same for queries, keys, and values, right? But what happens in grouped query attention is that we have a different number of heads for queries and keys and values. So queries will have X number of heads, but keys and values will have different number of heads. So let's say the number of heads in queries are 4 and the number of heads in keys and values are 2, right? How do we even perform the attention calculation? Because essentially you need the same number of heads to calculate the attention. That's where we have this repeat KV logic. So what happens is, to perform the QK transpose, what we do is we repeat the head multiple times. So for example, this is head 1 of K and this is head 2 of K. So we create duplicate heads for both K and V. And what happens is, this is head 1 of query, head 2, head 3, and head 4, right? So head 1 and head 2 of query will get multiplied with a 2 copies of the head 1 of K. So the head 1 of K gets broken down into 2 copies and both get fed into the query state. So um, this makes sure that 2 query heads see the same KV heads during attention calculation. So it's very simple. You just take a tensor and copy it and create a duplicate. So if so what happens is, we store X number of heads, but we compute 2 times the number of heads that we store. So it's just a computation trick. And group query attention is very popular, and it was first popularized by the Llama family of models. And the Llama family essentially started this idea where we don't need to have the same number of heads for queries and keys, and we can queries, keys, and values, where we can have keys and values with separate number of heads and queries with a separate number of heads. And the code for this is very straightforward. Like, it's literally some of the easiest part of the whole thing. The attention remains pretty much the same. There's really no difference between this and any other attention module that you might have seen somewhere, right? Let's just close the config for now. Yeah. Repeat KV is super straightforward. We create a new dimension to duplicate the heads along the new dimension, essentially. And all we do is we just reshape it into whatever dimension we want, where we get the hidden state, we get the number of heads that we finally want to replicate to. And so if it remains the same, then we're just going to give it back the input that we got. Otherwise, we create we reshape and we copy it that many number of times and return that, right? And the attention part is super straightforward. The scaling is basically the root d that we divide it with. We can manually override this by passing it at runtime. And we have key states, and what we do is we repeat kv for the number of key value groups, and we repeat it n number of times so that we match the number of states that we have in our query. Now, if attention mask is not none, then we apply the attention mask, and we'll see what this is eventually, right? Most of you probably already know what causal attention is, where we essentially allow each token to only attend to tokens that came before it. And just a quick spoiler, but the encoder uses causal attention, but the decoder generates all the tokens at once. So the decoder essentially does not have causal attention. The decoder essentially has a bidirectional attention, which generates all the tokens at once. So uh, if the mask is not none, then we apply the attention mask or whatever. This is just the minus infinity thing, which most of you already probably know. And then we apply a softmax to the attention weights after calculating, after applying the mask, and then we can add a dropout if we want to. And then we have the simple part where we multiply the values with the attention weights. That is, again, all this is just basic attention parts, and we return both the attention weights and the attention outputs, right? This is just an example of repeat KV. So let's say we give an input of this like 1, 1 and 2, 2, and we give n repetitions to be 2. And what happens is when we print it, we can see that it's 1, 1, 1, 1, 2, 2, and 2, 2, right? So each head gets repeated how many ever times we want it to be repeated, right? So that's the group query attention part. This is now we might enter the more tricky parts of this where we define the encoder and the decoder and all these like crazy stuff. We have defined RMS norm, we have defined uh, rope, we have defined the text embedding layer, we have defined how group query attention works, how we repeat the KV heads, all that stuff. And now let's define the encoder and the decoder attentions. Because now we are getting into building the model itself. You can see how this model has an encoder and it has the denoiser is technically just a decoder. But let's define those now. This is a simple diagram of the encoder and the decoder. This is not the entire encoder and decoder, by the way. This is just the attention part. And notice how I've written here text attention, because this, as I said in the beginning, this model takes in both text and image as input, and we are only writing code for the text part, right? I'm not defining the vision encoder in this video at least. So this is the text attention part. This is where we put everything that we have made till now. We put it all together to form the attention. So it's pretty straightforward, and I assume most people understand how uh, attention works in simple transformer models. As I said, the encoder basically caches the K and V of each layer, and the decoder reads this cache and adds it as context. So the encoder has whatever hidden state it will have as its input, and then we have the Q, K, and V values, and then what we do is we norm it. Once we norm it, we can then we can apply the rope, but as I said, the rope is applied only to the Q and the K. The rope is not applied to V. As we can see here, it's just transpose, and in the other two cases, it's rope plus transpose. So here and here. Now, as we said, this part is really important to understand because this is how we change the shapes of the tensor. So the cube projection converts it from, so the input is 3 comma 16. Here q goes from 3 comma 16 to 3 comma 4 comma 4. That means there are 4 heads. So 16 is the hidden dimension, which gets broken down into 4 heads, with each head having 4 dimensions, right? But that's not what happens with k and v. These get broken down from 316 to 3, 2, and 4, because the number of kV heads is 2 and not 4. Same goes for V. It gets broken down into 3, 2, and 4. And we repeat along this dimension twice so that we can match this dimension. So we can make the number of heads same. They're not same by default. And that's where the grouped query attention thing comes into play. Once we do norm and once we apply rope to K and V, then before we do the attention calculation, we will cache these K and V values. And caching is nothing to it. It sounds very complex, but it's pretty straightforward. What caching does is it just saves it into the register buffer. It just saves the value into a register buffer so that the decoder can read it later. So here it's written 29 such attention in the stacked upon each other in the encoder, and similarly the decoder has 29 such attention. And the layer 0 of the encoder caches the K and V values, and the layer 0 of the decoder will read from the same cache. So all it does is the register buffer stores the value, and the decoder will just read that value. So the simple way to remember is the encoder can modify the cache, and the decoder can only read from the cache. It can't modify it. Once we're done with the caching, we then go ahead and calculate the attention that we have defined. And once we calculate the attention, we get the output. We reshape it back to 316. So we start with 316 and we end with 316, just like every other typical attention model. The input dimensions and the output dimensions of an attention block are same. Now, the encoder attention uses causal attention mask because the encoder sees the prompt that we give in I love coffee, what is the color of the sky, whatever that we ask. And when we write the input, we write it one after the other. It should not attend to the previous tokens because when I say I love coffee, I comes first, then love, then coffee. We write it auto-regressively, and we don't want it to look at, uh, we want the model to follow the same. So we apply a causal attention mask to the encoder. And now coming to the decoder, um, things remain the same. The decoder sees a different sequence. So here the sequence length is 3 because the input prompt had 3, for example. The decoder has a different sequence length because this is the same as the canvas length that we defined. So as we saw in the diagram, the decoder generates n number of tokens at a time. So that n value is what we call the canvas length. So the canvas length So the canvas length is what we refer to as sequence length here. So these two values are different. The sequence length here and the sequence length here are different, and that is by choice. It's not that I made a mistake or something here. Um, this sequence length corresponds to the canvas length and the number of tokens that we are trying to denoise at a certain time step. So we have 4, 16. The dimensions remain the same. The dimensions here are 16 and the dimensions here are 16 as well. Uh, same process, everything remains the same. We convert this to 444 and we convert this to 424 because the number of heads in query is 4 and the number of heads in key and value is 2. Once we do that, we do the whole norm and we apply rope to k and v. We do not apply it to the value. And once we do that, now is the important part. We read the cache from the encoder. This is where it's different from something like cross attention, typical cross attention, where we take the values and use it in the calculation directly. We take the key and value from the encoder and just use that along with the query of the decoder and we calculate. It's cross attention. This is not cross attention because what happens is we are appending it. So we can see here it's 2, 3, and 4. Right? 3 is the number of tokens, and we can repeat 4 is the dimension and 2 is the head. So we get the 2, 3, 4 untouched, right? Exactly how the encoder has saved it for the ith layer that we are on currently in the decoder. And we append that to the current K and V value. So the current K and V value is 244 and we append the 234 to the 244 to get a 274 because we are essentially appending along this dimension, the second dimension. So we get a 274 and then we get a 274 here because we append the same thing. We're reading the K and V. This is the KV cache basically. We're reading the K and V from the encoder and we are essentially appending it to the K and V of the decoder. And the Q values remain unchanged. The Q is purely from the decoder. There's no change there. So the Q is 444 and we can see it's 444 as well. The K and V becomes 474 and 474. So when we do a QKT, we essentially end up with 447. That makes sense. Then and we also know that V is basically 474. So when we do QKT and then softmax, and then when we multiply that with V, this 7 and this 7 collapse with each other. And we finally end up getting 4, 4, 4. And 444 again, we reshape this 444 back to 416 because that's how we started the calculation. And once we do that, we give that as the output. So that is the decoder part of things. So again, the decoder has the same thing. We start with a certain canvas hidden state and we end with the same shape tensor. And we do all the attention calculations. We read the cache from the encoder, we append it to the key and value of the decoder, and we put all of them together and we essentially create this output. The only difference is in this attention calculation, we use no mask, right? There's no masking. So all the tokens can attend to all the tokens. The reason is because we are generating all of the tokens at once, not generating it one after the other. So because of that, we can use something called as bidirectional attention, which was popularized by Bert and things like that, where every token gets to talk to every token in the canvas. So this hidden state is the prompt, that is the input that we give. And this hidden state is the canvas, that is the place where we are denoising this, where this model is denoising and creating an output. So this is how the encoder and decoder attention works. Let's also look at the code because the code is like important as well. This is the same diagram which I had in my iPad, and it's the same thing. I have written bullet points here, and this entire Jupyter notebook is self-sustaining. All the information that you need will be in the Jupyter notebook itself. So let's look at the encoder, and it's pretty straightforward. We define all the things first from the config file. We have this config file which Google has so graciously provided us on Hugging Face, and we read all the dimensions, the hidden dimensions, the canvas size, and all this information. And once we have all the information, we define all that here. We define the norms, we put all that. And the forward is very straightforward. We get the hidden states, and here we are talking about the encoder text attention. So we get the hidden state, we get the positional embeddings, and we basically apply the rotary positional embeddings for each of these layers, and we apply them only to the query, and we apply the rotary embeddings to the keys. We apply only to these two. We can clearly see we're not applying them to the values. And we calculate, we check for the dimensions, we reshape them, we do all that, the multi-head stuff. And once we do that, we can norm the values. Once we have that, this is the important part. If past key values is not none, then we take the key states and value states and we update it here. Pass them to the passkey values and we update. This is the cache part. This is the KV cache part. We take these two values and we save them in the passkey values so that the decoder can later read it. This is simple. We just apply the attention after that and we reshape it and output projection. Very simple. You can look at the diagram. It is very self-explanatory. It's projection. We reshape with view. We do a norm. We apply the rope and transpose it. And we append the K and V to the cache. We calculate the eager attention, I mean the attention for the group query attention, and we reshape and give the output. Right? It's the exact same thing in code. Now, the decoder is an exact copy of the same thing. There's like literally no difference. The only difference is that it reads from the cache. Everything else remains the same. We take the Q, apply rope only to K and Q. We don't apply it to V. We do the transpose. We do the view to essentially change the dimension to multi-head. And here's the difference. This is the part where, we read the KV cache that the encoder has done. What we do is if passkey values is not none, we call this function that says append to cache. Let's see what the function does. So the function, what it does is it reads the cache first. So based on layer index, so if you're on the 0th index, it will read the value from the 0th index. If you're on the first layer, we'll read the first index and so on and so forth. Now, once it reads that, it takes the current K and V values. Right? Because if we look at what we are passing it the key states and the value states that we have now, and we are also passing it the past ones from the encoder. So what it does is it appends the K and V with the K and V from the encoder. And that's what we can see in the diagram as well, this part where it gets appended with each other. So yeah, it appends these two, and along dimension -2 is the second last dimension. we discussed in the diagram, we can see along which dimension we are appending or concatenating, to be more precise. And once that's done, it returns the concatenated key and values, right? So we get the concatenated key and values and then pass that to the attention calculation. And we can pass the attention mask here, which is basically none, because it's a bidirectional attention. And we get the output, we reshape it, and we give that out. So it's exactly the same thing that we discussed in theory. This is the code for the same. So we have defined attention, we have defined the encoder text attention, the decoder text attention. Now is the next part, and probably the most it's not hard to understand, but it's a little complex from like a perspective. This is the mixture of experts part. Where we define the router, where we define the experts and all that stuff. So what really happens is inside the encoder, this is kind of how it works. Multi-head self-attention, that's what we just defined inside both the encoder and decoder, by the way. We have the multi-head self-attention, which is basically the group query attention along with the norms and the where we apply the rope and we do all those things. Then we have a add and a norm where we take the input and we take this output, add them together and norm them and then pass it on to next. Uh, what we pass this on to are two parallel branches in the model. So one branch is a dense multi-layer perceptron. Very simple. This is the simpler part. The other branch is a router plus experts. This is the mixture of experts. This is what we popularly call as mixture of experts. And now let's define these three things, right? Let's define the MLP and let's define the router and the experts. Let's understand why we need this in the first place. Then let's look at an example and then let's look at the code and it'll all make sense. Hopefully it's a little complicated, but yeah. So what is a mixture of experts? So a mixture of experts is a bunch of multi-layer perceptrons. So where each expert is a multi-layer perceptron. And essentially, if you have, let's say, the config defines there are 128 experts. That means there are 128 parallel multi-layer perceptrons. And each token gets to choose which expert it wants. So for example, if you have a prompt asking the model to do math, if you ask the model to do math, then there might be a certain set of experts which get activated because the task that you want to accomplish is a math related task. If you ask the model something that's maybe something from history about like the Second World War or something like that, there might be a different set of experts which get activated. And the combination of experts that get activated is also important. So the router does this job of checking which experts need to be activated, and the experts are just MLPs which parse the information and give it out. Let's look at an example. We'll keep it very simple. These numbers are like obnoxious from like a realistic point of view, but they're just there to make the math easy and to like understand it easier. So let's say we have three tokens, each have a hidden state of 100, 200, and 300. And we have three experts. To keep this very simple, generally each expert will be an MLP. So it's a sequence of matrix multiplications. But to keep this very simple, let's just keep each expert as a function that multiplies a number with 1. So it's an identity expert. So it just takes in an input and gives the same thing as an output. So it doesn't do anything, which is not, it's not how it works, but you can just imagine this to be an MLP which applies some other function to it. But for now, to keep it simple, let's just think of an expert as something that multiplies the input with 1 and gives the same thing as an output. Simple. And let's say we have three tokens and we have three experts, right? 0, 1, and 2. And what we need is we need the top two experts. So the top K here, the K value is 2. So what we're going to do is for each token, we need the top two experts. So let's say we have token 0 and token 0 has chosen these two experts in this order. So token 0 says expert 0 and expert 1 are perfect for it. And it gave equal weight to both 0.5 and 0.5. Token 1 chose expert 2 and 1 with weights 0.7 and 0.3. So token 1 says that expert 2 is the best token, is the best expert for that specific token. And the next best expert is expert 1 with 0.3. Okay. That's token one. Now token two says expert zero and expert two are what it thinks are the best experts for it. And that is basically 0 and 2. And we can see how 0 is a better expert because 0 has a higher value, 0.6 instead of 0.4. So now that we have chosen the top two experts, let's see what really is happening here. So let's define this. So token 0 has 0, 1 here as we have defined, token 1, 2, 1, token 2, 0, 2. If we create this, if we convert this information into matrix form, we'll get something like this. How this works is we are essentially grouping based on tokens. How this works is we have 0, 1. So the 0th index is 1 and the 1th index, the first index is 1 in the second place. So how this shows is that token 0 selected expert 0 as its first preference in the first slot, and token 0 chose expert 1 as its second preference. So we are essentially just converting this information into matrix form. Similarly, token 1 chose expert 2 as its first preference and expert 1 as its second preference, right? So the index shows you which expert it is, and the order shows you the preference of the expert, right? It's very important to wrap your head around this. This is very crucial, right? Similarly, for token 2, I'm going slow because that you can just 2x it if I'm too slow. Similarly, token 2 has chosen expert 0 and 2, and here 0th expert is the first preference and the second expert is the second preference. And these are grouped based on the tokens. So this row corresponds to token 0, this row corresponds to token 1, and this row corresponds to token 2. What we want is we want to group this with respect to the experts and not with respect to the tokens. And I'll tell you why. This will make sense. Just like stick with me for now. This will completely make sense. So this is how it looks. This is the same matrix as this. I just wrote it so that I can have a clean thing. And this is grouped based off of tokens. We want it based off of the experts. So all we are doing is, if you're a computer science student, you might know what a row major and a column major is, right? So essentially, one is indexed based off of the rows and the other one is indexed based off of the columns. We're doing something very similar to that. And we can call it token major to expert major, something that's indexed based off of the tokens and something that's indexed based off of the expert. So let's try to see how this happens, right? If we look at expert 0, what it says is expert 0 is chosen by token 0 and token 2 as its first preference. So token 0 and token 2 have 0 as their first preference. Similarly, expert 0 is not chosen as a second preference by any of the tokens. That's why the second one is basically completely 0. Expert 1 is not chosen by any token as its first preference, which is why all of these are 0. And expert 1 is chosen by token 0 and token 1 as their second preference. That is why we have 1 and 1 here. Pretty straightforward. Similarly, we do it for expert 2. Expert 2 has only token 1 which has chosen it as its first preference as an expert, which is why the first the middle one is 1. And similarly, expert 2 is chosen by token 2 as its second preference, right? That's why we have only 1 there. Everything else is 0. So what we have done here successfully is we have converted a grouping based off of tokens to a grouping based off of experts. Super crucial. We'll see why. Each expert is a function, an MLP, and in our case, it's just multiplication with 1. Let's go through what each expert does, and then let's go through the algorithm, and in the end, it'll all make sense. What each expert would want to do is expert 0 finds ones and reports their coordinate. So there are two ones here, and both their coordinates are 0, 0 and 0, 2. Torch.where does this exact thing, finds where a thing is and returns its coordinates. So top k positions and token ID. So 0, 0 and 0, 2 are what we get. Slot 0, token 0, token 1. So this is slot 0, this is token 0, and this is token 2. That's what torch.where does. So essentially, we are once we group it by the experts, we are finding which experts are active for which token. Once we do that, we go and collect token zero's hidden state and token two's hidden state. This is whatever, initially we had made a simple case here, right? Token 0, token 1, token 2. And these are the hidden states of all three. So 100, 200, and 300. Keep it simple. So the hidden states we know are 100, 200, and 300. And the hidden states for 0, 0 and 0, 2, which is basically the experts that were activated, the tokens that activated expert 0, we get those hidden states, which is 100 and 300, right? Because token 0 and token 2, 100 and 300. Now, we know the weight. We know how much each expert is weighed for each token. We have set these softmax values, right? 0.5, 0.5, 0.7, all these values. Now, we look up the same thing so now we look up the importance of each expert from this table. So we know that expert 0 was given 0.5 weightage by token 0 and 0.6 weightage by token 2. So we multiply that 0.5 and 0.6 with the hidden states. So 100, 300 gets multiplied with 0.5 and 0.6. And this entire thing goes through so the hidden state goes through the expert first, and in our case the expert is nothing but something that does not modify the function. It returns the same output. So if 100 and 300 go in, 100 and 300 come out as well. Normally it will be an MLP which will modify this number into something new. Now this output gets weighed across its weightage, that's 0.5 and 0.6, and we get 50, 180. So token 2's expert 0's contribution is 180, token 0's expert 0 contribution is 50. And expert 0 has nothing to do with token 1. And we can see that here, right? Token 1 has not chosen expert 0 for anything. So token 1 has no business here. So that remains 0. And once we get all three of this together, you get 50, 0, and 180. 50 and 180 because they are the weighted expert propagated hidden state of tokens that activated those experts. And now we repeat this for expert 1 and expert 2 as well. And we get these two. And what we do is we keep summing these together and we finally get an output of 150, 540, 540. That's very simple. 50 plus 100, 150, 0 plus 120 plus 420, 540, 180 plus 0 plus 360 is 540. Straightforward. Nothing too complex here. So the only thing you need to understand is the reason we do this grouping shift. We are initially grouping things with respect to the tokens and then we are changing it with respect to the experts. This is because we only loop once per expert now. Every iteration only adds to the rows of the tokens that picked the expert. So this is the part where I really want you to stick with me. So expert 0, expert 1, expert 2. Token 0, token 1, token 2. Token 1 could have picked these two in any order. Token 1 could have picked these two. Token 2 could have also picked the same experts. So what happens is if you go through each token, then you'll have to activate the expert, like you have to load the MLP, pass it through that, weigh it according to its percentage, and give the output. So each token will require its own time to load its own expert, pass it through it, and it's a lot of work. So what we do is we instead group them based off of the expert. So for example, expert 0 was only called by token 0. So we change the grouping based off of the expert so that then we can just pass all the tokens that chose a certain expert together into that MLP or whatever that expert is as a batch, and we can just get the output in one shot. So that is the main trick that happens inside the diffusion Gemma mixture of experts, right? Because each uh, each expert looks at which tokens selected it at what priority, and then we take all those tokens which selected a certain expert and pass them and through the expert one shot. So this is super good for computing. We save a lot of memory. Sorry, not memory. We are doing very GPU efficient operations here instead of activating experts per token. So that is the whole like shenanigans, if I might use that word, that happens inside this router and expert. And that's basically what happens here. And on the other hand, we have a dense MLP, which is very simple. Like it's not complex at all. The dense MLP is super simple. You get a hidden dimension. We have a gated linear here. We have a up linear here. Then we have an activation. We then multiply these two together. We pass that into a down linear and we get the output. Very simple. It's just an MLP where there is no selection of expert. There is no top K experts. There's nothing. We just have all the tokens come in. We have MLPs. We have a gated MLP for all of them. We pass it, get the output, and that's it. But the router and the text expert part is where all the like the crazy stuff happens. Let's look at the code and things might get clearer when we do that. Again, the notebook has the diagram and all the things that you might need to know about it. There's one very interesting thing is that the experts and the router and the MLP, all these things, they belong to both the encoder and the decoder. Both of them will use the same architecture. One very important thing is that the expert and router share the exact same weights. So when we load the model, finally, when we are done with all this and when we load the model, what happens is we essentially copy the weights of all the experts in the encoder, and we exactly use the same weights for all the experts in the decoder. And that is a design choice which Gemma has done. Phenomenal. Like we are essentially just using the same block across both. So the experts remain the same across the encoder and the decoder. So the things that experts might attend to in the encoder and the things they might attend to in the decoder are the same. And fantastic design choice, and the ability to do that is really like incredible. Um, uh, Again, we only use the GLU activation in this. We don't use the SILU one. The reason I've defined it here is if a certain model uses multiple activations, this is how you do it. You create a function which maps whatever activation you need to its function and essentially use the config file to switch between whatever activation you need. Text router, again, the code is very heavily commented so that it's very readable and you can go through each step very clearly. We define the norm, the linear, the parameter, all that stuff, and we have a per expert scale. And for now, it's just like torch.1, and it's a learnable scale for the output of each expert. We'll see what it is. Let's look at the code. The input of text router is a flattened hidden state. So whatever hidden state comes out of the attention, we flatten it out. The router doesn't care about the sequence structure at all. It treats every token in the batch as an independent row to be routed. So first we do a norm, just a typical machine learning thing to do. Once we do the norm, we do the scaling, which is a learnable parameter that we have, and we do another root, which is again just all this is just for numerical stability, right? None of this is like very technically impressive. The flattened hidden state is basically of this dimension, and what we are doing is we are just projecting it into this dimension. So this is just a technically a token input, and we are converting that to uh, the expert dimension input. So we have 10 tokens. Now we are converting them in from 10 comma number of experts, like 10 comma hidden dimension to 10 comma number of experts. So a 10 comma number of expert matrix shows you which expert each row or each token is essentially attending to, right? Very simple words. Um, so each of your token now has the probability distribution over all 128 experts if 128 is the number of experts that you choose. And what this matrix essentially represents is how relevant is each expert to this token. If we have 128 experts and we have 10 tokens, then how relevant is each expert to each token? Once we do that, we do a softmax so that all the expert scores add up to one. So if we have one token and we have 128 experts, so all the scores given to each expert by that one token adds up to one. And now, yeah, so as you can see here, now each token expert that sums up to one. Now we index only the top K experts and throw away the rest of the tokens. Since we have 128 experts, and let's say we are only going to take the top 8, for example, we're going to throw away 120 experts. So each expert is an MLP and we'll not be computing them essentially. So top K weights and top K indices. And this is like basically, I wanted to use the same thing that I used here, right? That you can like essentially go back and check this. It's the same naming convention that I've used in the explanation. And top K weights and top K indices. This is how we index the top K uh, experts that we have from the probabilities. And this is very straightforward. Like whichever has the highest softmax score, the K number of top K softmax scores will essentially be selected. So what was batch size? So what was sequence length number of experts is now basically sequence length and top K, because initially it was 128 and now it will become 8. Uh, the top K weights is then renormalized to add up to 1 again, because initially all the 128 experts add up to 1 and now we have taken only 8 of them, right? We want all of those 8 to add up to 1 as well, because for numerical stability and things like that. So we do something like this for renormalizing it. So we are just going to renormalize it by the sum of the 8 experts. And once we renormalize it, we multiply it with the per expert scale. That's just basically a learnable scaling mechanism for numerical stability. And once we have all this, we return the router probabilities, the top K weights, and the top K indexes. So this gives you the expert scores, the top K the top K expert weights, and the top K indices, top K expert indices. So that was the router, and now this is the expert, and the router and the expert together form the mixture of experts essentially. And so this is a collection of expert weights stored as a 3D tensor, and we define all the basic stuff first, and then we look at the forward, right? So we start with all zeros with because obviously we need to initialize the output. Once we have that, we calculate the expert mask. That means which experts were picked by which token. So this is basically just a one hot vector, because essentially each expert uh, can only be chosen once by each token. So this is just a one hot tensor. And then what we do is we do this dot permute thing. And what that is how we interchange the token and the expert dimension. As we had mentioned, we want to change the grouping. We want to change the grouping from based of tokens to based on experts. So that is how this permute works. This permute essentially changes the dimension where the experts come first and the top K and sequence length come later, because the input is of where the experts are last. And here we can see that the experts are first. Then this is the part where we see which experts were hit by which token. So only the experts that got picked by at least one of the tokens would essentially be recorded. So this saves us a lot of compute, because let's say expert 10 was not selected by any of the tokens, right? The 128 experts we have and the 10 tokens that we have, the expert 10, or let's say expert 15, or any of the experts which were not selected by any of the tokens, they will not even be loaded in the forward pass, will not be even be used for compute. So we are essentially saving a lot of clock time, GPU clock time, by not even computing them. Uh, this is this essentially the second. This is essentially the part where we save a lot of compute, and Once we do that, we need to change the grouping of tensors based off of tokens and to based off of experts. Uh, the reason we do that is because now we can just iterate through each expert. Each expert gets its own MLP, and that is what we have essentially defined here: gated up projection and the down projection. It's the MLP which corresponds to each expert. Because if you look at the parameters of this, it is number of experts, and this is the MLP dimension. So we have an MLP of this dimension which does this transformation, and we have it for these many experts, and we have the up for these many experts and the down for these many experts. So it's just a very simple MLP. Yeah, so once we have done all this, we can iterate through each expert, find which experts were hit. We have found which experts were hit for what token. Once we have that, what we can do is we can essentially do the torch.where, and this is where the entire hand calculation, or this entire thing that I've done, translates directly into code. Uh, if this is a little confusing, I totally get it. It is pretty confusing. I would highly recommend you to go through the theory and then go through the code, and you can just flip between both. You can write down the theory yourself and then just compare it with the code. So what happens is we take the top k positions and top k index, and that is exactly like what happens here. And we can look at the weight, and then we are doing this part. We pass the hidden state through the expert and wait with the output for each expert. And that's exactly what's happening. For each expert, we take the hidden states of all the tokens that were activated by that expert, and we pass that through our MLP of that expert, and then we multiply the output of that expert MLP with the weights of whatever expert sat at that position for that token. And then what we do is we keep adding it. So we do this for each expert. Load the expert, we find out which tokens activated it at what order, and then we collect all those tokens which activated the expert, pass them through the expert, get the output, weight according to the softmax value of whatever, and then we take that and keep adding that. Once that is done, we can finally return the output of this, right? And this is basically what we are doing here. And the block diagram kind of mirrors the hand calculation, and the code directly mirrors the hand calculation as well. This is the trickiest part of the model, in my opinion, because there's a lot of, I like to call it dimensional gymnastics. Right? There's a lot of gymnastics we are doing in terms of the dimensions of what we're doing. And the MLP is very straightforward, right? As I said, the MLP we are talking about is essentially, just this thing. It's just a gated, skip connected, gated MLP. So we just define what the gated up projection is and the down projection is, and an activation function. The activation function we use is basically just the GLU function. And once we do that, the forward is super simple. We get an input X. We pass the input X through gated up projection, the gated projection and the up projection parallelly, just like how it's here. We get the input, and this part happens parallelly. And then we basically multiply the output of both those projections, pass that through an activation, and then pass that through a down projection. Very straightforward, super simple. But the hard part is all this, the expert part. If my explanation was too fast or too slow, you can like slow down, go through the code, go through the comments, go through the theory again, and things might like make more sense. So yeah, the text router and the text expert part is a direct copy from Gemma 4, which is why I've defined it as Gemma 4 as well. And the diffusion Gemma basically just inherits this, and it's exactly the same. There's no differences at all. And now we're getting into like the real stuff, right? So this is each encoder text layer. So what we had defined before was the encoder text attention, and the layer is essentially the combination of the attention, the norms, the MLP, the expert, and the router. Um, so this is where we put it all together, right? Essentially, this diagram that you can see, oh, it's like so messy now, but this is the encoder text layer, and there are 29 layers like this. So uh, let's just look at that. This is very straightforward. You just define all the classes in the init, just like how we have defined it above. And this is the forward, right? Forward is very straightforward. It gets the input of the attention block. We do a norm, just like any other thing. We calculate the attention, which is the text attention logic which we had written before. This also takes care of the KV caching part because we've already written the logic for it internally. The next two lines, we refer it together as add and norm. It's very common attention architecture, and it's a skip connection from the first hidden state to the normed post attention state of the model. Here, we have created a copy of the hidden state inside this residual. So what we do is we do a post attention layer norm of the hidden states, which comes out of the attention, and then we do a skip connection here with the starting tensor. Once we have that, again, we prepare ourselves for the next skip connection that we'll have to do. And then we have these two parallel branches. We go through two parallel branches of the block. One is the dense MLP and the other one is the mixture of experts, the router plus expert part. Uh, this is just a pre-forward layer norm. Again, just an RMS norm. Just the naming convention is different. Then we pass the MLP and we pass it through another norm. This is just the dense MLP, which is the branch one, right? The easier part. Now, this is the branch B, the mixture of experts branch. So hidden states, we flat it out. We get the residual, we flat it out because we give the flattened version to the mixture of experts. Once we do that, we essentially we pass it through a layer norm. Again, all these norms are just RMS norms. These are all just scaling and computation and stability tricks. Once we do that, we pass the hidden states to the router and we get the top K index and the top K weights. And once that is done, we pass the router output to the expert and we pass the hidden states to the same as well. Um, Once we do that, we can reshape it back and we can do one more layer norm. And once we do that, we can combine the information from the MLP and the experts, the mixture of experts. Essentially, both the parallel branches, they basically just get summed together. Once we do that, we have one more layer norm on top of that. And then we have the residual connection, which comes from here. So both the attention block and the mixture of experts and dense, the parallel block, both of them have skip connections to the state where it was before it started. Then we finally return the output. We have a layer scaler, which is not that important. It's just numerical stability. If you look at the layer scaler here, it's just torch.1. Now this doesn't really do anything. And we just multiply it with that and we give the output. That's literally the encoder block. Literally easy, like super easy. Uh, all the masking, all that stuff is taken care of inside the attention. The mask which we give is basically we can give a causal mask because it's the encoder, if you remember. And the decoder, you'll see, one second. So we look at the decoder in a bit. But before that, let's look at the encoder model, right? Because the model is basically a stack of 29 attention layers. Um, So the model is super simple. We have the scaled embeddings, which we discussed in the beginning. We have how many ever number of text layers, encoder text layers that we need. Again, we have norms and we have rotary embeddings. We have rotary embeddings. The forward is very straightforward. We get the embeddings. We pass the token IDs to the embedding layer. And once we have that, we start the dynamic caching. We This is to initiate the KV cache for each layer. Yeah, once we do that, we essentially have two types of masking for the sliding window and for the full attention. So these are two different attentions that this model uses. So if I have to give you a quick overview of what it is, sliding window, sliding attention is something that does not attend to the whole sequence. There's a certain a plus minus amount of tokens to which a token can attend to, and full attention is something that attends to the entire sequence. So full attention is the more typical attention that you might come across in like your typical models. Sliding attention is something where you only attend to k number of tokens before the token you're on and k number of tokens after the token you're on. And the mask is very simple. If you look here, the mask is just a basic like causal attention mask, right? The Pytorch already allows us to, Transformers already has a masking utils, right? If you want to create a sliding window mask or a causal mask, you can just directly call it. Um, so we have this, and we can now, once we have defined all this, we can go through each layer. The for loop where we go through each layer, we apply the rope values to the Q and K, and we cache the K and V values. So that is just this entire block where we are going through each layer. We are looking at what layer type it is. So is it sliding attention? Is it full attention? Based off of that, we decide which rope we want to apply, because sliding and rope, one uses proportional and one uses default. So we look at what layer type we are on. We apply the mask according to whatever layer type we are on, and we load the rope according to whatever layer type we are on. And once we have all this, we just apply the rope, we just forward pass through the layer with whatever mask we need. And once we get that, we get the hidden states and we give an output, right? Encoder output is just a dictionary. If you look on top, it's a name tuple, right? It's very similar to dictionary, but yeah, it's just a format of giving the output, like it's like a JSON or whatever. Um, and the diffusion Gemma encoder model is just, so the reason, okay, this is the diffusion Gemma encoder text model. As I said, we are not loading the vision module. I'm not loading the vision tower. So we still need to match the state dict that the model has, because I need to load the weights from whatever Google has provided. And that's the only reason I've created this class. This class essentially sets the text model as the language model, and we do not define the vision model at all. And the forward function is just a simple self.forward. So this whole uh, forward that we have defined here, it's literally the same thing. Let's look at self-conditioning before we go to decoder, because self-conditioning is used inside the decoder. And the decoder is almost the same as the encoder. The code is basically the same. The only difference is the self-conditioning that we add. Um, so let's look at what self-conditioning is. It's literally just a small gated MLP, and it takes the previous denoising step decoder output logits, and it softmaxes them into probabilities and mat multiplies them. This gets this gives us a probability weighted blend of embedding rows. Now let's see what this means. Like, so complicated. Let's see what it means. Um, so the later steps can build on and sharpen earlier guesses rather than re-deriving things from scratch. So in the beginning of the video, I had mentioned about how there might be certain tokens that it's not fully confident on, but it's somewhat confident on. And we want to give this signal forward to the next iteration of denoising. So that's why it's called self-conditioning, giving its own output in the next iteration. So let's say we are at denoising step 10, and we are on our way to 48. If we set it as 48. So before we go to 11, what happened is we have noise sky, noise blue. Right? These two have been locked in. They are accepted tokens. But these two are still requiring some time. So what happens is this noise token, the model is fairly confident that it is the sky is blue is, let's say that's what we are going for. So the model is pretty confident that it is the token that needs to come here is and it's like 70% confident. But also it could be a sky is blue is also a valid word. It's a 0.1, etc. Like, so there are like certain tokens, the model is very confident that it is pretty much that token there. So how do we convert this? The soft embedding would be zero 0.7 multiplied by the embedding of the added with 0.1 multiplied by the embedding of a. How it works is, so here we see, right? Softmax them into probabilities and mat multiply them to get the probability weight blend of the embedding row. So we softmax to get these, and then we multiply that with the embedding and add all of them together to get this uh, a blend that represents model uncertainty from the last denoising step. This blend gets added to whatever noise token 0 currently is, and then gives to the decoder as a hint in the next step. So when a model gives the output and we go to the next denoising step and give the same thing to the decoder, it will have this conditioning signal which allows it to uh, retain some level of information on the how the previous iteration went. So that's what self-conditioning is, and the code is also very simple. In my opinion, the hardest part of this model really is the mixture of experts part. But anyway, so self-conditioning, super straightforward. We have a norm, we have a gated projection, we have an up projection and a down projection. Right? And super simple, we get an input, we just pre-norm it. We have a down projection, and the way we do that is first we pass it through the gate, we pass it through the up projection, both parallelly, multiply their outputs, and pass that to an activation function and given to a down projection. If you might think this code is super similar to something that we have already done, it's because the MLP in the encoder has a very similar one. The encoder in the MLP has a very similar one. And yeah, so the gated MLP concept is like super common in this model across multiple different components. And so in the forward function, yeah, as we discussed, we norm it, we pass it through the gated MLP, we get the self-conditioning signal, right? It's the output of the MLP, and then we add that back to the input embeddings. And then that combined thing gets normed, and that is what we return as an output. And this is what we use within the decoder. Now we can define the decoder, and the code is exactly the same as the encoder. So there's nothing, it has an identical topology to the encoder text layer. Only the attention class differs because it reads from the cache instead of writing to the cache, and the self-conditioning part. But that self-conditioning part comes later in the model. Let's just define the decoder for now. So how each layer looks like, right? So again, same code, exact same code. The only difference is that in this part, right, we do attention. Within the module, we are calling the decoder text attention, which is basically something that reads from the cache. So the code is exactly the same. It's nothing, no big deal about that. Now let's define the model. This is where things get fun. This is the model. This is the final model that we're going to be using for whatever that we want to use it for. So let's define the class, Diffusion Gemma decoder model. And this is the model that does all the denoising and all the cool stuff. Encoder just encodes the prompt. The decoder is what does all the the cool stuff, right? So uh, we get the scaled word. We have embedding layer. We have a bunch of decoder text layers based on how many ever we want, 29 in the Diffusion Gemma model. And we have rotary embeddings, and we have self-conditioning. So we define this function called create diffusion decoder mask, and it's very straightforward because all we have to do is just return none because it's a bidirectional attention. So we don't really use any mask anyway. So super easy there. And once we have that, let's go through the forward function. And because this is where this is where the magic happens. Right? So we get the input, we get the input tokens, I mean, in the ID form, and then we get the embeddings of whatever that is. This input is the canvas, right? Encoder's input is the prompt, but this input that we are talking about is the canvas. The canvas is where we are denoising and we are predicting all the tokens at once. So those two are very different things. I just wanted to mention that. Now, self-conditioning. If self-conditioning logics is not none, that means it's not the first iteration. If it's not the first iteration, then we'll have to do something. But let's see what if it is the first iteration. So if it is the first iteration, we just create a bunch of zeros. We just assume the self-conditioning signal to be zero. But then the self-conditioning does not contribute at all to the next denoising step because there is nothing to self-condition on. It's the first step. If it's not, then as I said, we need to do the math merge. So first we take the self-conditioning logits and then we softmax them and then we matrix multiply them with the embedding tokens. So just like how we saw here, we uh, take the softmax, and multiply it with the embedding. And that's basically what we do here. And Once we get that, we multiply our embeddings with the self-conditioning mask, which you can define uh, runtime you can define this during runtime and pass it through the model. And then once we have all this, we have the input embeddings with the self conditioning stuff, right? Pass it through the self conditioning, the MLP part of things. Because we've calculated the softmax, we've calculated the conditioning signal, we've calculated soft embeddings. We pass that along with the input embeddings. That is whatever the canvas has now, and the soft embeddings are what it had in the previous iteration. Once we pass that, we get the final input embeddings where you have the canvas embeddings along with the flavor of what the previous canvas looked like. And yeah, so if it's the first iteration and random canvas was not generated yet, because that's how we do it, right? We generate a random canvas first, then we go ahead and create a random canvas, and read from the cache to get whatever the prompt is, right? Because if it's the first step, we need to see what the prompt was to even start decoding. We do all that stuff. We get the passed keys from cache sequence length from this is basically where we are reading the prompt, the encoded version of the prompt from the encoder, from the cache, from the KV cache. And then we have the blank canvas that we generate. And once we have done all the basic stuff, we are essentially ready to like do the decoding. Uh, then we can basically just go through each layer of the decoder and pass the canvas sequence along with the prompt. So once we have all this, we can essentially go through the decoder and just pass each layer. Each layer would essentially take care of all the passed keys and all that, the reading from cache and all that stuff is taken care. We already defined all that stuff before. Once we have that, we can just norm and we can give the output, decoder output most of the stuff is pretty straightforward, right? Decoder mask is basically just none. So that helps out. We need to know which layer type we are doing and all that, just like how we do it in the encoder. And we need to define rope and all that stuff. Now, finally, we're at the model. This is where, this is what I think everyone came here for. And let's define the model. And the model follows a very simple very, not simple, but like, yeah. We encode a new prompt. We get the cache and we decode it. We randomly initialize if nothing is there, and then we decode it iteratively. So the model is pretty simple. We have an encoder and we have a decoder. And the forward is basically just calling the encoder first, where we are calling the encoder here. And once the encoder does its job, then we can move on and use the decoder. And we use the decoder with the self-conditioning, obviously. And once we have that, we can give the complete output. The output, there are three things that we return here. That's the last hidden state. That's the decoder's output, which obviously is what we need to predict the canvas. And passed keys, yeah, that's the KV cache. And the encoder's last hidden state, this is just metadata, which we'll use later. Now, if you look at the model on the website, right, you'll see that there's an LM head here. So once the output from the decoder comes out, there is a language model head which selects which token, because the decoder output is just a bunch of logits. And we don't want logits. We want an attention. We basically want tokens that mean something to us, right? That's what the LM head is. So the LM head is nothing. It's just a linear layer which converts the hidden size to the vocabulary size. So what happens is it converts the logits to the vocabulary. It's like how embedding layer converts the like how embedding layer converts the word into an embedding. This one converts an embedding into a word. It's like an inverse operation basically. And we have a soft capping value, which is just a scaling thing in Diffusion Gemma. It's 30. We'll see where it's used. So model is straightforward. We call the self dot model, and the model is the Gemma Diffusion Gemma model, where we go through the encoder and the decoder. And once we get the model outputs, which is one raw score per possible token for every canvas position. If you have a canvas length of 5, then we have 5 possible positions being predicted at a time. The LM head goes through this output and uh, con essentially converts them to a vocabulary based score. The reason why this is important is because eventually that's how we select what the token is, what word belongs to the token. Um, yeah, so once we do that, there's something, once we pass it through the LM head, which is just a linear layer, we actually have a very interesting trick which Diffusion Gemma does, is it divides the logits by this soft capping value, which is like 30 in our case. And then we pass that through tanh, and then we get the output of that and then multiply it with the final logits. So we divide by 30, pass it through tanh. So it brings it to the range of minus 30 and 30. And then we multiply it by 30 to essentially invert the division operation that we have done before. This is again a numerical stability thing. I'm not very sure as to why they do it, in all honesty. If somebody knows, please mention it in the comments. But from what I understand, it's just a stability trick and it keeps it continuously differentiable, unlike a hard clamp. So if you do a hard clamp of taking a certain value and just cutting it off, it's not really differentiable. But if you do a tanh, you can squash it and you can still keep it kind of continuous everywhere. And then we just give the block diffusion output. So this is the diffusion part, but we still need to like perform the diffusion. And now it's a good part to really go back to the initial uh, part where I explained, how the model works. So if you go back to this part, and we'll basically be coding this part. And if you have any confusion, go back to where I explained this and just go through it once so that you understand what I'm trying to do here, right? And yeah, so very straightforward. Uh, this is the part where we do the diffusion, iterative denoising of the canvas using the encoder and decoder so that we can finally get a prediction. Entropy bound sampler is straightforward. As it's written here, it initializes a random canvas, accepts the lowest entropy tokens, and entropy is just an inversely proportional value to confidence. So if you're very confident on something, it has very low entropy because you're certain. Because entropy represents uncertainty. So if you have high confidence, you have low entropy. If you have low confidence, you have high entropy. Um, Initializing the canvas is just a random initialization, just like how you initialize a random Gaussian. We provide the vocabulary size, the canvas length, all that stuff. Uh, Once we have that, we define the function for accept and we define the function for renoise. And the accept is straightforward. Um, we create a categorical distribution of all the logits that we have. So it treats the last dimension as the outcomes and everything before that as an independent batch of separate distributions, all evaluated in parallel with zero Python looping. If you don't know what a categorical distribution is, I would highly encourage you to check that out. I can't really get into uh, like the math of that. It's like a separate topic altogether, right? Um, but it creates a categorical distribution. So in very simple words, what a categorical distribution is something like this. A categorical distribution is essentially you're just talking about a Gaussian distribution where you have high confidence values, you have low confidence values, and if you integrate over it, you essentially get one. So that basically is what a categorical distribution is, and then we sort it. So once we have this distribution, we create, and we are creating this categorical distribution out of the logits that come out of the the LLM head, right? LM head of the model that we discussed. And then we calculate the entropy. So entropy is just inverse of confidence. So however confidence it is on a token, we just get the inverse of that. And most of you probably know the formula of entropy already. It's probability multiplied by log of probability. I uh, log pi. And once we calculate the entropy, we sort it according to the entropy. Going back to the same example as we did here, we have a bunch of categorical logits, and then we are sorting them in the ascending order. And that's why here you can see descending equals false because we need them in ascending order. And then we calculate the cumulative entropy. cumulative entropy because, again, if we go back to the example, we said we define something like a budget, which is 0.1 in our case, and then we keep adding numbers along this direction until we hit the budget, and then we just cut off and we accept everything on this side and we reject everything on the other side. So we do the cumulative sum, and what we do is selection. We create a selection mask where that mask exists for all the sorted entropy values, where the entropy value subtraction of the cumulative entropy remains below the bound. So all the tokens which are until whatever bound we have set for the entropy, we select all of them. Once we have that, we create an accepted token mask to know which tokens we accepted. And torch.where is just how we check where the location of the selected tokens are. We need to know because when we sort it, we lose the location of the token. We need to know where it is. So we just do that. And the renoising is just an extension of that, where we create a renoise mask, which is everything that is not selected. So if we take the accepted tokens and if we do a tilde, then we get all the rejected tokens. And once we have that, we create a random mask for it. And wherever we find the renoising is required, we essentially do that. We pass this mask so that we can renoise it. Straightforward. This is just the temperature scaling thing is just a way to control the diffusion. So if I had to explain it, right? Let's say we have, let's just say we have 40, let's say we have 48 steps. So we have 0, 1, 2, 3, so on until 48. So at the zeroth step, if it is very confident about something, we don't really want that. We don't want our model to be super confident about something. So what we do is we can scale this Gaussian into a smaller Gaussian by just dividing it with some scale. So we can either, so any Gaussian that we have, we can either spread it out or make it more sharp. Oh, sorry, that's bad. Make it more sharp. So the way we do that is by using something like this. So what this thing does is, late in the block, temperatures approaching Tmin are divided by smaller numbers that sharpen the distribution towards near deterministic. And the earlier in the block, many steps will sit near Tmax. So it's just a scaling value which looks at which denoising step you're on, and it basically squishes the categorical distribution or it stretches it. It's more sharper or it makes it more less blunt. The stopping criteria, as I mentioned, is very straightforward. There are like two things which we check: the overall entropy across the whole canvas. If it has completely gone below the budget of whatever we have set, we stop the prediction. Or if we get an EOS token, we stop it there as well. Right? Those are the two things. So that's just what we do here. We calculate the distribution entropy, and if it's less than the confidence threshold that we have set, that is the average entropy across the whole canvas below the confidence threshold. If it is, then cool. Then we good. And this is the generate function. This is where the whole denoising happens. So let's go through step by step. We already know how the model works. It's always important to keep that in mind because that gives you perspective of why we are doing something. So generate. Um, An entropy bound sampler, we initialize it because that's what samples the random noise and random canvas, renoise, and all that stuff, right? And then we have a stable and confident stopping criteria, and we start the denoising. So how this model works is a very interesting thing. So a question that might come to your mind, like, let's say, hey, do you like coffee? Is a question that you want to ask. And the output is, yes, I like coffee, but I also like tea. So let's say the output is yes. So let's say the output is yes, I like coffee, but I also like tea. So what happens is this is a canvas, right? We are denoising it and canvas of length 4, and we are denoising it and like all that stuff, like we get that. But we need this as well. Like this part is also part of the output, but the canvas is over. It cannot be limited by the canvas length. So what this model does is, once we have finalized this canvas, let's say all the tokens have reached a very stable entropy and we can confidently predict all the 4 tokens, we append this canvas with the prompt. And this whole thing now becomes the new prompt. And then we create a new canvas uh, of length 4. Technically, this has 5 tokens, so we can actually just create it like this. So what happens is, then we generate, this is canvas 2. But for canvas 2, the prompt is this, the whole thing. And then we iteratively go through 48 steps of denoising. And let's say we finally conclude with this. This is now confirmed. So now this entire thing, let me use a, so now this entire thing is the new prompt. And this is the canvas. So this is the new canvas now, and we initialize with random variables. And for this canvas 2, oh sorry, this canvas 3, this is the prompt. So what happens here is that we initialize an empty canvas and we go through denoising. What will happen is all these will end up with EOS tokens. All of them will just be EOS tokens because the sentence ends at T. So, so within the third canvas, we are essentially able to complete the denoising. Once we hit the EOS tokens, we can stop. So what happens is we get a prompt, we create a randomly initialized canvas, we iterate through it, we put it back to the prompt, now create the big prompt, I create a new canvas and keep doing the same. So that's what happens. And so yeah, we initialize the canvas and we go through each step in reverse order. So we go from 48 to 1, not from 1 to 48. That's just the typical diffusion style of, iterating. And we have the model. We get the decoder outputs. Once we get the decoder outputs, we use the temperature schedule thing, that is based on which step we are on. So the temperature schedule takes in which step we are on and the raw logits. And as I mentioned before, we have this thing which can essentially scale based on what step we are on, right? Scale the logits. So we do that. Once we do that, we have the processed logits and we do a softmax on them to get the probability. This tells us which token from the vocabulary the model is even talking about. Then um, Then we sample a stochastic guess and compute a greedy guess on what the argmax is which token that we are talking about. So the model might have 3 or 4 tokens with high confidence. Right? High is a relative term, but like higher confidence. It'll use those confidences as a multinomial distribution and it'll sample from that as to which word it should be, right? Once we have that, we just check which tokens were accepted, which of them require denoising, and we check if things need to stop because have we reached the stopping point, right, based on the criteria that we have defined. Then we calculate the self-conditioning logits for the next loop because the denoising happens loop by loop and we need to pass on these self-conditioning logits to the next loop in order for it to make the next guess. We don't want it to guess that from scratch. We wanted to have some sense of what happened in the previous iteration for it to be able to make the next guess. Uh, Once we have that, most of it is pretty simple. We concatenate, append the finalized canvas, and move to the next block if canvas length is finished. So as I mentioned in this example, if one canvas block is not enough for a certain output, then we can have a next canvas initialized for the same. And we can keep going until we check if an EOS is generated or we can stop generating the further blocks. And that's the code. That's the code for the whole model. I know this video is like huge, very long video, and there's a lot of concepts happening. But yeah, just a small thing. This is the part where you remember I told you how the weight inside the expert and router for the both the encoder and decoder are the same, exact same. So because both of them have the expert MOE layer, and the encoder and the decoder both have the same experts in them. And this is the part where we essentially go through the encoder and decoder and make sure that we have the same parameters in both. This function basically copies the weights, not really copied, but it basically is the same. We make sure that both those blocks are the same block. They refer to the same thing in memory. We That's what this tie encoder decoder weight does. We pass the model and we make sure that both the weights refer to the same thing in memory. This is just the config, just defining all the things. Obviously, this entire config will get overwritten by this config when we load it. And again, all of this is just config defining stuff. And once we have defined all that, yeah, so this cell is basically purely for myself. I have two RTX 3090s, and both of them are like 24 gigs each, right? So I wanted to split the model across both the GPUs, and some of it still remains, so it'll go onto the GPU, on the CPU. And so I just wrote this custom logic to split the weights and different modules across different devices. So this model splits different modules onto different devices, and so that I can just load the model on GPU, right? The model is like huge. And in the end, what we do is so don't copy this function. This entire function is literally for my setup, and your setup might or might not have the need to do that. Then we have the final infer diffusion Gemma model with the original weights function. This is the function which loads the weights and does the denoising and inference and all that. So we take an input and we apply the template so that we can pass it as an input to the model. And we have the generation config and all that stuff, like how many steps do you want to denoise and all that. And we can finally call this function with a certain prompt. And you can see I just gave a simple prompt here. Hi, can you write a code for MNIST for classifier and train a LoRa? Just write code for training a LoRa as well, things like that. And what it does is it goes through the whole thing step by step. It loads the prompt, and you can, if you just make it scrollable, so that you can now see it prints the entire code that I might need for this task. The code I wouldn't say is very accurate, but that's all good though. We can see that the model clearly works. It gives the output. It goes through each step, and it goes through multiple canvases and multiple denoising steps for each canvas, and finally gives me this code output that I had asked it for, right? And we can see how the entropy changes through steps and all that stuff, right? Finally, when stop becomes true, the model stops printing and model stops denoising, and we can see the output that it prints here. And this is just the canvas, final canvas that it prints. You can see the last ones are all ones because they are EOS tokens, because the final canvas was not fully required for the output, right? And that's about it. That's the model. This video is super long, and I'm like, I hope people were able to follow through with what I'm saying. Please go through the code again and again. Go through the concept, go through the code, try to write it yourself. I hope this video helps. Anyway, peace.